Hey everyone, today I'm going to revise solid state chapter of class 12 chemistry. So to start with, we need to know what is difference between crystalline and amorphous solid. Okay? So these are the characteristics of crystalline solids and these are characteristics of amorphous solids. Now crystalline solids, they have definite shape, sharp melting point, sharp edges on cutting, definite and characteristic heat of fusion, anisotropic in nature. They are true solids and they have long range order. Example NaCl, quartz. Amorphous solids, they have irregular shape, melt over range of temperature. They're basically opposite of crystalline solids. Okay, irregular edges on cutting, do not have definite heat of fusion, isotropic in nature. Pseudo solids, that is false solids. Short range order, example glass, rubber, plastic, quartz glass. Okay. Now, next we move on to the classification of crystalline solids. Now, crystalline solids are further classified as molecular, ionic, metallic, and covalent. In molecular, they are further classified as nonpolar, polar, and hydrogen bonded. Now, let's see the characteristics of these solids as well. In molecular solids, in nonpolar, they have soft insulator, very low melting point, London or dispersion force. Example, you can take the I2, CO2, argon, and CCl4. Now, polar, they are soft, insulator, low melting point, dipole-dipole interaction. Example, HCl, SO2. Hydrogen bonded one, they are hard, they are insulator, low melting point, hydrogen bonding between the molecules. Example, H2O. Okay. In ionic solid, they have the characteristics they are hard but brittle, insulators in solid state but conductors in molten or aqueous states. Okay, because in molten state they have become ions due to which they will help in conduction. Now they have high melting point and electrostatic force of attraction between the particles. Example NaCl, ZnS, CaF2. Okay. In metallic solid, they are hard but malleable and ductile. They are conductors, they have high melting point, and metallic bonding. Example iron, copper, silver. Okay, you can see this kind of solids in elements, right? Now, in covalent solids, they are hard but graphite is soft, exception. Insulator but graphite is conductor, again an exception. They have very high melting point, covalent bonding. Example SiO2, quartz, diamond, graphite. Now the next part we move on to is what is crystal lattice? Okay, and unit cell. What is unit cell? It is smallest part of lattice which can be repeated in all directions to generate the entire lattice is called as unit cell. Example if you see we can see a cube over here. Okay, so now, if we generate the same cube in all direction, we can generate a unit cell. Okay, as per definition, if we generate in all directions, we will get a unit cell. Okay, so the small cube is known as unit cell because if we repeat in all direction, we'll get a crystal lattice. Now the seven prominent lattices are cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, triclinic. Okay, and to remember the axial length as well as axial angle. Okay, so I know most of you get confused in remembering the axial length and axial angle. So you can just remember that. See, first initially they are equal, then one will be unequal, then both will be unequal. Again repeat it. Then one will be unequal, and then all equal, and the last one is all are unequal. Okay, remember the starting one is all equal and the last one is all are unequal. Okay, in the axial angle you can remember is 3, starting 3 is equal and that is equal to 90 degree. Okay, and the last one is all are not equal, 90 degree. Okay, now we know that there are 14 3D lattices which are known as Bravais lattices. Okay, Now, in unit cells, they categorize into primitive unit cells and centered unit cell. In centered unit cell, they are further classified as BCC, body centered unit cell, and FCC, face centered unit cell. Okay. Now we need to know the number of atoms in unit cell. Okay. So in primitive unit cell, that is simple cubic unit cell, the atoms are only at the corners. Okay, so in a cube we know that there are 8 corners. Okay, so 8 into 1 by 8 equal to total 1 atom is present. Okay, in BCC the atoms are at each corner and 1 atom at its center. Okay, body centered cube. Okay, body centered unit cell. Fine. So see, at the corners there are 8 into 1 by 8, that is 1 atom, and in the center is 1 atom. So 1 plus 1, that total 2 atoms. Okay. In FCC, that is face centered unit cell, atoms are at each corner and at center of all the faces of the cube. So it's known as face centered unit cell. Okay. So 8 into 1 by 8, that is 1 atom. Now there are 6 faces into half. So that 3 atoms. So 1 plus 3, that is 4 atoms. Okay. Now we move on to the closed pack structures, that is 1D structure, 2D structure, and 3D structure. In 1D structure, we can see that each atom is combining with 2 other atoms. So the coordination number is 2. In 2D structure, we have square closed packing and hexagonal closed packing. Okay, square closed packing, all the atoms are in the same style they have been made to settle. Okay, made to combine. So they're like A types. Fine. And the coordination number is 4 because each atom is combining with other 4 atoms. Okay. In hexagonal close packing, we can see that it is in a different way as compared to square close packing. Okay. And we can see that each atom is combining with 6 other atoms. So the coordination number is 6. And type is ABAB type because see, if you see the first layer and the second layer, it is not of the same style in which they are made to settle. Okay, so it's ABAB types. Okay. Now in 3D structure, we have simple cubic packing, that is AA type, this one. Okay, it's in 2D and if you make it as a cube, then it will be a 3D. So AA type and coordination number is 6, means each atom is combining with 6 other atoms. Now in hexagonal close packing, that is HCP. Okay, in 3D there is the second, the structure is hexagonal close packing, HCP. Okay, it is covering the tetrahedral voids. Okay, so it has ABAB types, ABAB types, ABAB types, and the coordination number is 12. Now in the cubic close packing or face centered cube, you can say it as FCC or CCP. It is ABC type. See, this is the A, this is the C, and this is the B. You can see that all three are different, and it covers the octahedral voids. Okay, so coordination number for this also is 12. Now we move on to types of voids in 3D packing. They are tetrahedral and octahedral. Okay, tetrahedral void is between the 3 atoms space, and the octahedral void is the 3 atoms and the way of arranging the other 3 atoms upon it. Then the space between them that is left is octahedral void. Okay, so number of atoms in CCP slash SCP, if it is n, then remember that number of octahedral voids will be n and tetrahedral voids will be 2n. Okay. Now remember in ionic solids, anions, that is bigger ions, they form the closed pack structure, and the cations, that is smaller ions, they form the voids. So many questions are formed and they mention the anions and cations. Don't get confused in that. Always remember that the cations occupy the voids and anions occupy the closed pack structures. Okay. Now we move on to packing efficiency. Okay, that is a percentage of total space filled by particles. Now, just remember this, it's very useful in competitive exams as well. Okay, they often ask these questions in NEET and JEE. So, in packing efficiency, for simple cubic, it is R equal to A by 2. Okay, and then for BCC, it is R equal to root 3 by 4A. In FCC, it is R equal to A by 2 root 2. And the packing efficiency for simple cubic is 52.4%, For BCC, it is 68%. Okay, and for FCC, it is 74%. The formula of packing efficiency is volume occupied by n atoms divided by total volume of unit cell into 100. Okay, so remember these formulas, it's very important. Okay, they're often asked in board exams as well as competitive exams. Now we move on to radius ratio. Okay, now this is it's asked in competitive exams mostly. Okay, and not is for, it's not for boards. Okay, so ratio is the ratio of cation by ratio of anion. Now in the usually in questions they generally give the radius ratio and they ask you the coordination number. So it's important to learn these ranges. Okay, if you learn it 2 3 times you'll get it. Fine. And the structure also they often ask. So if the radius ratio is from 0.155 to 0.225, the coordination number is 3 and structure is triangular planar. Example you can use B2O3, boron trioxide. If the radius ratio is 0.225 to 0.414, it is coordination number is 4 and structure is tetrahedral. Example ZNS. And then if radius ratio is 0.414 to 0.732, the coordination number is 6. Structure will be octahedral. Example rock salt. If the radius ratio is from 0.732 to 1, the coordination number is 8 and structure is BCC. Okay, an example is cesium chloride. So it's important to remember this. Okay, now they'll directly ask the coordination number or the structure. So you can learn it. Now we move on to the other part, density of unit cell. So what is density? Density equal to mass by volume. Okay. Now this formula it is very useful in board exams as well as the competitive exams. In this, they will give you you need to find any one of them. They'll give the four of them and you need to find any one. Fine. Okay. So see, this is the it is given by default. Na is Avogadro's number which you need to remember. Okay. And they will give you any three and you need to find the other one. Fine. So density equal to just remember the formula. Z into M by A cube into Na. Z is the number of atoms per unit cell. M is the molar mass. A is the edge length and Na is the Avogadro number. And D is the density of the unit cell. Many questions are asked in this formula itself. It's important to remember this. Now we move on to imperfection in solids. Okay, so the defects in solids, now they are basically of two types, point defects and line defects. Point defects, they are defect around a point or atom, and line defects, they are defect in a row. Okay, and they're divided into three types, stoichiometric defect, non-stoichiometric defect, impurity defect. Stoichiometry defect is no change in stoichiometry, but there is a defect. Okay, in non-stoichiometry there is change in stoichiometry, and in impurity defect there is a presence of foreign atom, that is any other cation. Okay, now we'll see all the three defects in a very detailed manner. In stoichiometry defect, okay, we'll see non-ionic solids and ionic solids. Non-ionic solids, okay, in stoichiometry defect they're also called as intrinsic or thermodynamic defects. Okay, now in non-ionic solids there are vacancy defect and interstitial defect. In vacancy defect, some of the lattice sites are vacant and which leads to decrease in density. But in interstitial defect, there the extra atoms occupy interstitial sites. Okay, and they also increase the density. Now, interstitial sites, it basically means that some of the ions they occupy this space. Okay, you can say it as they come in between, which increase the density of the unit cell. Okay, now in ionic solids, there are two types: Frinkel defect and Scotty defect. In Frinkel defect, smaller ion that is cation move from original site to interstitial site. Okay, they show vacancy and interstitial defect. That is vacancy in the original site and interstitial defect in the new site. They are also called as dislocation defect. Okay, and density doesn't change but because they show both defects, vacancy as well as interstitial defects. Now they are shown by ionic substances in which there is large difference in size of ions. Example you can say AgCl, ZnS, AgBr, AgI. Okay. In Scotty defect, the number of missing cations and anions are equal. Okay, they only show vacancy defect. They lead to decrease in the density of the substance because there is vacancy defect over here. Example is NaCl, KCl, AgBr, CSCl. Now, important thing to remember is AgBr will show both the defects, Frankel as well as Scotty. So it's important that they will give the options and they'll ask which of the following will show both defects, Frankel as well as Scotty. So it's important to remember the example. Okay, it shows both Scotty and Frankel defect, AgBr. Now we move on to non-stationary defects. Okay, there are two types: metal excess defect, metal differential defect. Metal excess defects, there are further two the reasons. First, due to anionic vacancy. Okay, in this, excess of cations and anionic sites are occupied by electrons, which are called as F centers. Okay, F stands for Faber center. Example is NaCl, LiCl, and KCl, and they also they have their own colors. Now, the other reason due to the extra cation at the interstitial sites. Okay, and they're observed on heating metal oxides like ZnO. When we heat it, okay, it lose electron and turns into yellow. Initially, it was white. It has okay, both cations and electron move to interstitial sites. Okay, important example is ZnO. Fine, it will change its color from white to yellow. Now, in the metal deficiency defect, okay, it is due to variable valency of metal. Example, we take as FeO, okay, which is found as Fe0.950. Okay, it's a basically variable valency. Understand? So due to this, it is metal deficiency defect. Now, in impurity defect, it is due to presence of foreign atom, that is any other ion. Example, Sr2 plus in case of NaCl. Okay, if we are in the foreign atom is Sr2 plus, which occupies the place of two Na plus ions. Though the charge is balanced, but it will lead to the vacancy. Okay, it occupies height of one ion and the other side remains vacant. It balances the charge, but the other side is vacant. Okay, it's basically due to the foreign atoms or any other atoms. This impurity defect. Example is NaCl, CdCl2, AgCl. Now in hexagonal structure, the important thing you need to remember is radius is a by 2, number of atoms is 6, coordination number is 12, packing efficiency is 74%, octahedral voids is 6, tetrahedral voids is 12. Many questions can be easily solved with this knowledge itself. They'll mention the hexagonal structure and they will ask any of these things. So it's important to remember these. Now the last part, which is asked in many competitive exams, some cubic ionic solids. You need to remember, okay, some ionic solids which they ask in the competitive exams usually. Example, the rock salt NaCl. You need to remember that Cl minus will occupy the CCP structure. Na plus will occupy all the octahedral voids. Okay. Example AgCl, AgBr, NH4Cl. In this, Na plus is of 4 atoms and Cl minus is 4 atoms. Need to remember this. In CaCl type, okay, Cl minus will occupy at corners, Cs plus will occupy the cubic void. Example CaCl, CsBr, CSI. Already one of the JEE questions has asked this NaCl. So if you don't know this, how many atoms and where do they occupy, you won't be able to solve the question. Fine, and Cs plus is 1 atom and Cl minus is 1 atom. In zinc blende, ZnS, S2 minus occupies CCP structure. Zn2 plus will occupy alternate tetrahedral voids. Okay, and there are 4 atoms of both of them. Okay. Now in the fluoride structure, CaF2, Ca2 plus CCP structure, F minus all tetrahedral voids. Anti-fluoride structure, in that example is Na2O. The Na plus will occupy first 4 atoms, O2 is 8 atoms, and the negative ions will occupy CCP structure. positive ions will occupy all tetrahedral voids. Most importantly, you can remember the starting of the two types. Okay, it's very important for the competitive exams. Okay, but you can refer all the five for future use. That's all from my end. If any other query, please write in the comment section below. Thank you.